Hello, the learning objective for this video is to be able to graph rational functions based on transformations of the parent function. So the parent function in this case is going to be f of x equals 1 over x, which you actually saw in Algebra 2a. So first, pause the video and fill out the following table of values. One for positive values of x, and the other for negative values of x. All right, when you filled those out, you should wind up with something like this. A couple interesting things here. When you do f of 1/3, that would give me 1 over 1/3, which would give me 3. So f of 1/3 is 3. F of 0, more interesting, would give me 1 over 0, which is undefined. So now we're outside of our domain. X is not allowed to be 0. So now using these tables of values, you'll notice they're similar on the negative side. These will be in the first quadrant. These will be in the third quadrant. Graph the parent function. Pause the video. Give it a go. Actually pause the video. If you didn't pause the video, please pause the video now. Okay, so it has this shape. It passes through the point 1, 1 and -1, -1, and it never touches the x or the y axis. These are called asymptotes. In this case, x cannot equal 1. So along the x-axis, we can put in this dashed line to show that we approach this value but never actually reach it. This is called a vertical asymptote. And we write asymptotes as equations. So in this case, the equation of this asymptote would be x equals 0. That's a vertical line. X will be fixed. X equals 0. The y-axis is called a horizontal asymptote, or HA is how we're going to abbreviate it. And the horizontal asymptote also should be expressed as an equation. That'll be y equals 0. So this is the parent function. It contains the point 1, 1, -1, -1, has vertical and horizontal asymptotes, and contains all of these points. Based on what you know about transformations, try to graph this. Pause the video and give it a shot. Okay, so here we're going to have a vertical asymptote, x equals 2, a horizontal asymptote of y equals 3, and those are shown with the dashed lines. It's a good idea to dash your asymptotes in first. And then we have to shift all of our points to the right 2 and up 3. So what was 1/2, 2 will wind up being 5/2, 5. And if we put these points in, there'll be a point here, a point here, and extending up. There'll also be a point right there, and extending out. Make sure to put arrows on the end. And similarly on the other side. It's good to label some points. If you want to get really careful, you'd want to label, I would say 6 points in this case. But if you have them listed off to the side, that would be okay also. Okay. Oh, that's out of order. That's out of order. Let's try this one. Based on your understanding of transformations, try to graph this one. There's an extra wrinkle in this one. Give it a shot. Okay, this has been shifted 4 units up and 1 unit to the left, so our vertical asymptote is now x equals -1, which is this dashed line right here. And our horizontal asymptote is y equals 4. And we have a vertical reflection. There's a negative multiplier on our argument, so we have a vertical reflection also. So what used to look like this is going to be reflected vertically. And now it's going to look like this in some fashion. Vertical reflection. Our points have been shifted and reflected, so what was 1/2, 2 is now -1/2, 2. Is that right? I guess so. 1, 1 will now be 0, 3. If you put these points in, 0, 3, negative 1/2, 2. It'll look like this. And you can label some of these points. 0, 3 is a good one to label. Oh, that was ugly. Deal with it. And that would be the point, negative 2, 5. So here we have two translations and a vertical reflection. But what we haven't seen yet are dilations. Try this one out. Can you graph this based on your understanding of transformations? Pause the video, give it a shot. Okay, here our asymptotes haven't been moved at all. There's no translation, so we still have our asymptotes at x equals 0 and y equals 0. But we have a dilation, and this is a vertical dilation. It's happening outside of the argument. It's affecting the output of the function, which means all of our x values are going to stay the same, but our y values are going to change. 2 becomes 6, 1 becomes 3, 1/2 becomes 3/2, negative 2 becomes negative 6, and so forth. And if we graph this, did I do that right? No, that's wrong. Right there, and right here. So this is a much more taller, wider, both those words don't make a lot of sense to me right now, but if you show a couple points right there, this point of 1, 3, and then this point of negative 1, negative 3, and perhaps a few other coordinates off to the side or put into your graph with labels, that would show your understanding of dilations. So this is your first dilation. Often dilations make these a little bit trickier. What used to be in the parent function over 1 up 1, one way to think about it is it used to be over 1 up 1 from this point 0, 0 is now over 1 up 3. What used to be over 1 down 1 in the parent function is now over 1 down 3 in this dilated function. So now let's put dilations in. Try this one out. Pause the video, give it a shot. Okay, dilations often make this trickier, so just take your time with it. We have our translations give us a new vertical asymptote of x equals negative 3, which is this vertical line right here. We have a horizontal asymptote of y equals negative 2, which is this horizontal dashed line right here. Put your asymptotes in first. And then if you do your translations, your dilation, if we have a vertical dilation of 2, because we've multiplied by 2, vertical dilation of 2, what used to be over 1 up 1 is now over 1 up 2. So the over 1 doesn't change. So that gives us the point negative 2, 0. What used to be over 2 up 1/2 is now over 2 up 1. You see that? What used to be over 1/2 up 2 is now over 1/2 up 4. So we get a dilated graph that's a bit taller. And similarly on the other side, a bit taller. And the parent function, again, starting from here, what used to be to the left 1 and down 1 is now to the left 1 and down 2. What used to be to the left 2 and down 1/2, see how I stopped there, is now to the left 2 and down 1, because we're multiplying all of those vertical outputs by 2. That's what a dilation does. So that is graphing rational exponents based on transformations. A little bit tricky, but with a little bit of practice, you should be able to get this down.